In this work, we explore how will actor-critic methods designed for learning in fully observable environments generalize to learning under partial observability. We consider different actor-critic algorithms, as well as different forms of partial observability and environment complexity that the agent may be presented with.
Partially observable environments can be framed as partially observable Markov decision processes, also known as POMDPs. POMDPs contain the same components as traditional MDPs, only they do not reveal the true state to the agent. Instead, agents are given only partial observations of the true state and must exploit future expected returns based on belief states. There are three main methods for solving reinforcement learning problems. Value-based methods approximate the true value function of the environment and generate a greedy policy from these estimates. These methods bootstrap their approximations by using previous value estimates to generate new value estimates, which result in lower variance. However, value-based methods may not generate an optimal policy, even when the approximations are accurate. Policy-based methods search for optimal policies directly, which result in better convergence guarantees due to the policy gradient theorem, but tend to be high in variance. Actor-critic methods combine both methods, using approximate value functions to critique new policies. This results in lower variance while also maintaining some convergence guarantees.
We focus our work on continuous control tasks. Specifically, we use well-established Majoko benchmarks implemented within an OpenAI gym environment to perform the experiments. To convert these MDP environments into POMDPs, we employ a wrapper environment which alters the observations given to the agent. We specifically examine noisy and faulty forms of partial observability. In a noisy POMDP, Gaussian white noise is added to the observations given to the agent. In a faulty POMDP, a random subset of the observation dimensions is obscured. The algorithms that we use for our evaluation are twin delayed deep deterministic policy gradient, or TD3, soft actor critic, or SAC, and proximal policy optimization, or PPO. These are all continuous control algorithms that have achieved good performance across many tasks, with some distinguishing features between them. TD3 focuses on training deterministic agents with a number of variance reduction techniques. SAC is a maximum entropy framework, encouraging its agents to take actions as randomly as possible. PPO focuses on constraining policy updates and can easily be extended to the discrete control setting.
For our experiment, we evaluate the performance of each algorithm in both types of POMDP. We ensure that the noisy environments are comparable by using the same seed for choosing the obscured observation dimensions, and use their performance in a traditional MDP as a base for comparison. We observe that our implementations in the MDP case perform similarly to their respective original implementations in the same domain for both SAC and TD3. We now show episode rewards for SAC in the Majoko environment, followed by videos of the best performing agents for each action, and do the same for TD3. Note that there are no results for PPO. This is due to the fact that we were not able to get our implementation to converge to any optima within our time constraints. We observed that SAC performs significantly worse in the POMDPs, but is noticeably better in the noisy POMDP than TD3, which shall be shown later. We believe that this is due to SAC having a maximum entropy objective, which may result in less noise sensitivity.
TD3 was completely enabled to learn a non-trivial policy for noisy hopper, as well as for noisy ant to a lesser extent. TD3 adds noise during training for target policy smoothing, but its lack of entropy maximization likely makes it less resistant to additional noise than SAC. Unlike in the noisy POMDP setting, in the faulty POMDP setting, TD3 was able to produce better results than SAC. TD3's superior performance in the faulty POMDP case may be indicative of a superior ability to extract hidden information from a state space. For all domains and algorithms, the agents trained in the faulty POMDP setting were able to produce better results than those trained in the noisy POMDP settings. There was also a considerable difference across benchmarks. Across agents and settings, there was a greater percentage drop in performance for Hopper than for Ant. We attribute this disproportionate performance drop to the smaller dimensionality of Hopper, resulting in greater effect on the agent's perception of its state. In the future, we aim to complete our PPO implementation and update the results and conclusions accordingly. All updates will be available in the linked repository.